So I'm going to be talking about the link between black holes and their star formation rates. So to get everything in context, we know that the red sequence grows as you get to lower redshifts. We know this through things like the UVJ diagram. If we take a population at one redshift and the next, and you can count them and you can see that the red population grows. And this implies that galaxies transition from a star-forming phase to a quiescent phase, right? So the question is, how do they do that? How do galaxies stop forming stars? Yes. That's fine. Yes. So how do galaxies stop forming stars? And specifically, I'm going to be focusing on central galaxies. And this is because satellite galaxies actually undergo very different processes. And I think distinguishing between them is very, very important. And as you saw in Joanna's talk, they are different beasts, right? So this is what we usually think of a galaxy as, just the luminous parts, right? But in actuality, there's a lot more happening out in the halo that we can't really see very well unless you study it. And so this is a hot gas around it. And the hot gas has the potential to cool. And when it cools, it goes down to the middle of the potential well, the bottom of the potential well, and it can fuel star formation in the central galaxy. And what could stop cooling? That's the next question if we're looking at this. And a number of physical mechanisms have been proposed, and all of these probably happen in some way or another. But I'm going to be focusing on AGN feedback, and that's actually what models typically generally use in order to stop their star formation in their models, and for good reason. When we look at the halos, such as the one that we were looking at here as like a little toy model, we look at them in the real universe, and we see that AGN feedback affects these halos. And so here are other examples of the radial lobes embedded within the cavities of these galaxies, hot halo masses. And it's been shown that this kind of AGN feedback and the evidence of cavities happens just as often in isolated group as well as cluster environments. And so this isn't just happening in the largest BCG galaxies as many people think, but actually probably goes down to lower regimes as well, lower mass regimes. So my question is there a link between the galaxy's black hole mass and the star formation rate? How do I attempt to answer this question? Well, I look at the physics. So the physics is telling you that there must be a heating and a cooling, right? The heating from the black hole and the cooling from the galaxy's hot halo mass. And so I use 3 observable galaxy parameters in order to parameterize this and plot them against each other. So one is the black hole mass, directly detected black hole mass, dynamically. And so this black hole mass is telling you about the heating, and then I use the stellar mass to tell you about the cooling, because we can't really get halo masses for these galaxies, right? And so we're using stellar mass as the best proxy. And then the battle between heating and cooling actually gives you the resulting star formation rate. And so I use these 3 parameters, black hole mass, stellar mass, and star formation rate, in order to kind of probe the effects of the black hole on the star formation activity in the galaxies. So here, I choose central galaxies that have dynamically detected black hole masses. Here, again, this is kind of like the heating term. Here's the cooling term with stellar mass. And you see a positive correlation with a bunch of scatter. So when you compare these, so here you have just black points. But then if you color them based on this specific star formation rate, depending on whether they're star forming or not, then you get this. And so you have you have quiescent galaxies living in a different and distinct part of this plot than the star-forming galaxies. Namely, quiescent galaxies have more massive black holes than their star-forming counterparts. And so we can compare this to models, a bunch of different physically motivated models. And as you can see, at first glance, all of them are very different. They have different normalizations, scatter, slopes, etc. But I'm not concerned with that. The qualitative differences about where, dealing with where the blue and red points lie, are actually very sensitive to the AGN feedback physics that is happening in the models. And so I don't really have that much time to explain all of the physics, so please come ask me about it. But Qualitatively, we find that the Munich and illustrious model are more closely resembling observations because they have red points and blue points lying in distinct parts of this plane, namely that the red points are at higher black hole masses than the blue points. Unlike in Eagle and Galaxy, where Eagle overlaps, and they both overlap their distributions. Sorry? Yes, but the blue points overlap over the red points. And that's showing you that Eagle uses short mode, quasar mode feedback, and this isn't actually sufficient to keep a galaxy quiescent. In illustrious and Munich, you have a constant inflow of heating, and so this is really necessary in order to keep the galaxy quenched. In Galaxy, you have a halo mass threshold, which does not agree with the observational results that we have. So, yeah. So we find that there is a link between the galaxy's black hole and the star formation rate. But in actuality, our star formation rates actually run throughout the whole kind of range of specific star formation rates. So kind of labeling one as star forming versus quiescent in this middle range here. Not working, but in the middle range, it may be too simplistic. And so we really want to look at the star formation rate, the specific star formation rate, and how it varies with black hole mass and stellar mass. And so we do that, and we find that the specific star formation rate on the y-axis is a smoothly declining function of the black hole mass and stellar mass ratio, or what we call the specific black hole mass, or what you can think of as a black hole prominence. So how prominent is the black hole in the galaxy? And this indicates that somehow the specific star formation rate knows about the black hole in the center of the galaxy. And so there could be two ways in which this is possible. So basically, they could either be causally connected or they're connected through a separate but related process, right? And as I showed before, there has been no successful physically motivated model that shows the second scenario. And so I'm going to be assuming the first scenario when I'm creating this kind of formalism in which we can think of this framework in which we can think of what's happening physically in these galaxies. So I set up a little illustration here. We have 3 galaxies in our sample. All of them have dynamically detected black holes. You can see that you get a small black hole and then larger black hole as you get to the right. All of these have the same stellar mass. So if you recall, I'm using stellar mass to kind of tell you about the cooling, right, in the galaxy. And so you see that the cooling should be the same in all of them because their stellar mass is like the same. But the black hole is telling you about the heating. And so big black hole, lots of heating, meaning that there's very little cold gas that gets to the galaxy, whereas at the low black hole mass, there's a lot of gas that gets to the galaxy because there's just a little bit of heating versus a lot. And in the middle, you have some cooling because you have a medium-sized black hole, a medium-sized black hole prominence at least. And so if you plot these on our main plot of specific star formation rate versus the black hole stellar mass ratio, again, these are all at the same stellar mass, and they're all lying at different parts of this plot, telling you that quiescence is not dependent on stellar mass directly. It should correlate with it, right? And so the black hole really matters, and the black hole stellar mass ratio. So with the rest of our galaxies, this is similarly has a large range of morphologies, types. It spans a large range of stellar masses, black hole masses, specific star formation rates. And so if this is actually widely applicable, then it's telling you something about the way that galaxies transition from active to from star forming active galaxies to passive galaxies as well, because in my framework that I just laid out here, does not require the galaxies in the intermediate part of the star formation rate space to be transitioning at all. If you have a galaxy that lies in this middle part that has a medium-sized black hole compared to its stellar mass, then it can stay here in this middle part of the diagram. It doesn't have to be transitioning. So my framework kind of says that, and there's been a lot of multiple kind of sources of support for this argument, whether it's been Omler et al. 2017 or Eels et al. 2017, which argued that star formation rates are not good for anything that's off the star forming main sequence, or if you want to look at longer time scales. For example, Belfiore's talk earlier today was talking about different timescales. Pandya also was talking about it, Barro, Wu, etc. And so I urge people to think about whether they're assuming that they're transitioning, or whether they actually know that these galaxies are transitioning, and how we can measure that. And so more research needs to go into actually figuring this out. But yeah, and so in summary, I've shown that the distribution of star-forming and quiescent galaxies lie in distinct regions of this plane, the black hole mass stellar mass plane. And this is telling you from comparison with the models that a semi-continuous source of heating is needed in the form of radio mode AGN feedback, in the form of some kind of black hole feedback that's long-lasting and long-term, and affecting the galaxy's hot gas around it continuously, right? And I also showed that the specific star formation rate is a smoothly declining function of black hole mass over the stellar mass. And this is telling you that partially quiescent Green Valley galaxies might not actually be transitioning, and they might actually be quite stable. And so more kind of research needs to go into that and seeing if they're actually transitioning. And in addition, kind of looking at heating versus cooling gets to the physics of quiescence, and specifically degrees of quiescence, which I argue we should be looking at rather than either quenched completely or star forming completely, because we need to look at that middle region and see what kind of degrees of quiescence are possible, what kind of timescales for quenching are possible. Yeah, so thank you. That's right. It's a little puzzling. So the way that I kind of think about it is looking into models such as Eagle, which use this kind of quasar mode feedback. So it's more like quasar mode in the sense that it affects the gas inside of the galaxy. And it's only when it's actually accreting that it heats up that gas. But in other models, such as in Enriquez, it's a more continuous mode of heating. And so this I kind of explain, and in Illustrious that's also the case. And I think in Illustrious it works in that it creates these bubbles that expand into the medium. But those bubbles keep expanding into the medium and heat up the hot gas around it, even after it stops accreting. And so that's how it kind of continues its heating cycle, even though the black hole isn't feeding. Does that make sense? So the heating is continuous, but the feeding doesn't have to be. So I want to ask how you define quiescent galaxies. So I think what you're asking is, am I arguing about the transition time between blue galaxies to red galaxies, right? And you're saying that there's a bimodal distribution, right? So then there is that. I'm not arguing that there's no transition. I'm arguing that some galaxies might not be transitioning within that region. Yep. Yes, because the black hole grows fast and gives you a large black hole mass stellar mass ratio. So I'm not exactly sure how fast that is, but it has to be fast enough to give you this kind of relation on the specific star formation rate versus black hole mass stellar mass relation, right? Because we don't see galaxies on the top right or lower left part of the plot, the black hole really does have to work. There's some kind of time scale that has to be at work, but I haven't really figured that out yet. And the scatter tells you something about that as well, right? Thank you.